Good afternoon, all. So, welcome back to our webinar. Now we will start for our next talk. So, I am happy to extend a warm welcome to Professor Niharika Mahapatra, Professor at IIT Bhubaneswar for more than 10 years. She received her PhD in 2006 from IIT Bombay and completed her postdoc for 3 years at TIFR Mumbai and 4 months postdoc at IIT Bombay. She achieved Young Scientist Award from Board of Research in Nuclear Science in 2012. She has more than 46 publications in Referred Journal and 20 peer-reviewed publications in Proceedings of Conference. Her research interests are magnetism, multiferroics, spintronics, superconductivity, and thermoelectricity. Today, the title of our talk is Proximity Effect in Exchange Bias Coupled Biomagnetic Nanostructures. With this short introduction, once again I would like to welcome Professor Niharika Mahapatra Madam to deliver her talk before us. Thank you, ma'am. Please share your screen and proceed.
Thank you, Deepika. I will first share my slides. Is it visible?
Yes, madam.
Yes, ma'am, it is visible.
Yes, madam.
Okay. So, thank you, Babita madam, and all the faculty members present here for giving me this opportunity to talk to the students and faculties of this institute. So without wasting any more time, I'll start my talk. Okay. So as already mentioned by Deepika, that the title of my talk is Proximity Effect in Exchange Coupled Biomagnetic Nanostructures. Am I audible? Please respond.
Yes, ma'am.
Yes, madam.
Okay. So, because I was told, I just came to know that there are many students attending the seminar. So, most of my slides, I have tried to make it as simple as possible and try to put more fundamentals rather than applications or rather than more of the research slides. I'll first introduce what I'm going to say. So, after introducing, then I will talk about magnetism at nanoscale. Then, what is superparamagnetism and why it arises due to the surface and interface effect? What are the effects that change the magnetic property? And I pick one of the proximity effect, that is the exchange bias effect, and particularly with the system of magnetite and nickel oxide system. So before going to these details, I'll introduce my lab. So basically we work on correlated electron system, and these are my PhD students, and the work that I will present is mostly done by my student Soumya Gandapanda. So some of the research facilities that we use, I have only given one or two, but there are more to explain over here. So the research activities that generally we conduct is interface control quantum materials, photovoltaic based application of correlated materials. We also work on unconventional superconductivity, van der Waals materials, and magneto-optical sensors. So these are some of the topics that we right now carrying out. Now with that, let me proceed towards a brief overview of magnetism in solids. So this gives you a brief overview. Why I say brief overview is that in a nutshell, I am telling you what all kinds of magnetism that you see in solids. So as you all must be aware that diamagnetism is intrinsic property of all matter. But apart from that, the entire magnetism we can divide into two parts, the localized and the itinerant magnetic system. The localized system, what is basically the difference between these two? The localized system or the localized magnetism is basically the magnetism associated with the electrons or the spins which are localized in their orbitals. Whereas the itinerant system are here, just bring the pointer, okay. So this is the itinerant magnetism is basically the magnetism associated with the mobile electrons or which are movable, which freely move like your free electrons. So this is associated with the conduction electron. Now further, if we look at the various types of localized magnetism, that is your traditional magnetism that you already study, like your Curie paramagnetism, ferro, antiferro ferrimagnetism. On the other hand, the itinerant magnetism also exhibit Pauli spin paramagnetism, band ferromagnetism, and band antiferromagnetism. Because here, since the electrons are mostly mobile electrons, so you don't directly calculate the moments like we do by using Hund's rules in case of localized magnetism, because they are already in their orbitals. Whereas in case of itinerant magnetism, since they are free or mobile, they are not localized at one place. They, due to hybridization and all, they can share their orbitals or they can move to another orbital. So basically, we study that in terms of band. So by looking at the band structure of metal, we have to decide on the magnetism. And there is also another kind of diamagnetism, that is Landau diamagnetism. This has been discussed mostly in case of 2D electron gas. So there also we talk about free electrons. So that is also a kind of itinerant magnetism. So this is overall magnetism in solids that we find. It's all traditional. Now, it's such an old field. It's known since the Lordstown age, that is quite long back. So such an old field. So why do we study it? Still, we keep on studying. Still, we look at different kinds of material and all. All this is because of their application. Since long ago, we have been applying this. These are the traditional application like electric motor or some rotor or permanent magnet, like that we keep on applying. But most of the advanced application that you will find in information technology, in memory devices, your RAM, your magnetic hard disk. So we try to make more compact. We try to miniaturize things. So all these are possible because of the technology that we find on the application of different kinds of magnetism that we do. So then this is something that you already have studied in your book, so I will not elaborate much. You have the conventional paramagnetic ferro-ferri and antiferromagnetic system. So I will not elaborate much. I hope all of you might be knowing this. But how do we categorize that? It's based on their response to the applied magnetic field. So if you apply magnetic field to certain materials, so how do they respond? So their response can be positive, negative, or linear or non-linear. It is linear. Generally, paramagnets are known as linear magnetic materials. And other systems like ferro, ferri, and antiferro are non-linear systems. And their chi is for ferro ferri chi is very large. For ferro it is the largest, then the ferri and all that. So for diamagnetism it is very small and negative. So this is how it responds. But there are certain magnetic systems that some of the recent discoveries. So certain systems where by looking at this response, you cannot really categorize what will be the magnetic property. And this comes under a kind of magnetic order that is known as your helical or spiral order. You will come to know why this order is so important. There is also another kind of disordered system, but order in disorder, that kind of thing, that is known as spin glass, which is like you can compare it with your normal glassy system. So like in a glass, glass is kind of amorphous, but at local, if you look at a particular point, so surrounding that you will find some sort of local ordering, but there won't be any long range ordering. So spin glasses are like that. If you look at in a particular area or so, you will find that spin is aligned along some direction. But then if you look at the entire global system, you won't find any sort of ordering. So this contains some sort of local ordering, not the global ordering. On the other hand, helical or spiral orders are kind of magnetic systems where you will find that it is neither ferro nor antiferro kind of ordering. The magnetic spins they are rotated with respect to their neighboring spin by a certain angle, and with respect to this, the other one is rotated. With respect to this one is rotated by the same angle. So like that, this kind of ordering is known as helical ordering. This is a conical spiral. So in a cone, you will find that this spin is getting rotated by certain angle, with keeping the angle fixed. So this kind of ordering is known as spiral ordering. So basically, what are these kind of ordering? And recently a name was given to this that is known as magnetic skyrmions. Hello?
Yes, ma'am.
Okay.
Ma'am, you please continue.
Yeah, tell me.
Okay, you please continue.
Okay. I heard some sound. I thought whether it is disconnected or something, because you are not able to see. So that's why sometimes get confused.
Yeah, ma'am. I will inform you. Yeah, sure. I will inform you. Now it is.
Jen is, yeah.
Madam, your voice is very clear and screen is also visible. Continue. Please continue.
Okay. Thank you. So these are certain kind of magnetic systems which are known as magnetic skyrmions. So what are these skyrmions? Like I had shown you that there are kind of like spiral or helical ordering. So here you will find that the neighboring spin is rotated with respect to any one spin. If you look at its neighboring spin is rotated by some angle. So they rotate in a particular fashion. And depending on that fashion, there can be Neal type ordering, there can be block type skyrmion or Neal skyrmion, or many like biskyrmion. Like that, there are different nomenclatures. So, but overall, why these kind of, so this is called a shrill of magnetic system. They form a particle-like structure. And why it is important is that if you look at this two-dimensional sheet, you can see this presents some sort of skyrmions. So they can be very important. Like if we get this as very small particle-like structure, they can carry the magnetic data. So they can carry the data, and they are very important in like quantum computing and many other types of application like data storage, data transfer, and all those things. So this, if we can get very small size magnetic scorpions, that will totally be revolutionized, and this will be non-volatile, consume less energy. So there are many advantages along with that. So basically, what is the origin of all this kind of different magnetic order? The origin is basically basically is the exchange interaction that happens between the two neighboring atoms or neighboring electrons. So we understand the exchange interaction by this particular equation. So this equation represents the interaction energy. So this is particularly the exchange interaction between two neighboring spins at ith and jth position. On the other hand, this particular term represents the interaction of the spins with the magnetic field. So I will show you, I mean, although I will not elaborate the details, but I can just give you a glimpse that if we look, write the corresponding Hamiltonian for this interaction, I mean, suppose we consider two atoms, let us say hydrogen atom, and then these are the two nuclei and these are the two electrons, and try to write the exchange interaction corresponding to these two electrons. So ultimately you will find that this represents the symmetric term and antisymmetric term. So accordingly you will see that this particular interaction is, I mean, the origin is electrostatic interaction and not magnetic. So you should remember, I mean, this is particularly for all the students that generally they ask that what is the origin of exchange interaction, because that gives rise to magnetic. So the most spontaneous answer happens is that it has magnetic origin. Although this gives rise to magnetism, but it has electrostatic origin. Okay, so this is for my students. Okay, now depending on whether the interaction is positive, interaction means I showed you this particular term Jij. So this Jij represents the exchange interaction strength between the spins Si and Sj. So whether this J is positive or negative, depending on that, your interaction between the two ions can be ferromagnetic or antiferromagnetic. So for this is, you can see from this plot, this A by R in the x-axis, it represents like basically the distance between the two atoms or ions in a solid. And in the x-axis, it is actually J. I'm sorry, this is J. It's not A. So this is actually J. J is the exchange interaction. Now this exchange J is whether positive or negative. If it is positive, you get ferromagnetic interaction. Now if it is negative, you get antiferromagnetic. So this is the boundary. You can see above this you get iron group elements which show ferromagnetism, whereas below this it is negative, so you get antiferromagnetism. And I'll show you one of the most other types of exchange interaction. So this, you can all have direct exchange interaction, you can have super exchange interaction or RKKY interaction. So this super exchange and RKKY interaction, there are also other kind of interaction like your double exchange interaction, or there can be DM interaction, Dylon-Moria interaction. So all those interaction apart from direct exchange interaction are indirect type of exchange interaction, and those are mediated by the ligand ions, or in case of RKKY interaction, this interaction is mediated by the surrounding conduction electrons. You can see These are the conduction electrons which are mediating the interaction between two neighboring spins. These are the localized spins. So whatever the interaction and all that, but you know that for any ferromagnet, the most I'll not this particularly I'm not discussing because this discuss the band ferromagnetism. Anyway, so whatever the interaction, but if you have a ferromagnetic material, this is a typical curve that you come across with. This is known as your hysteresis loop. Now, the question arises for ferromagnetic material or antiferro, for all these materials, exchange interaction is the origin of all this kind of order. So why do we find such kind of behavior? That again, what is this kind of structure that you all are aware that in any ferromagnet there will be domains like this. Now the question comes, why such kind of domain forms? Okay, so I'll show you why do domains form. These domains, now let us say that you have a particular material and where the spin is aligned, let us say all the spins are aligned in one direction. You have a material and there are no domains. So if we have some material like this, you will see that how will the field lines, like any charge or magnetic field, you all are aware of the field lines. So the field lines will be like this, and you can see some of the field lines are close, some are like this, which extend to long distances. So outside this material, you will find some sort of stray field present. If there is only a single domain or all the spins are aligned in one direction without any domain wall, you will see that there are so many stray fields. So these stray fields, now let us say that we break into domain. If we break into two different domain, you will see that the field lines come from one domain and they end at the other domain. So like this, the domains, forming of domain reduces the external stray field. So if you break further into other domains, so you will find that the outer stray fields reduces. So since this formation of domain reduces the stray field or demagnetizing field, so it is always energetically favorable to break into domains. So you need less energy to break into domains. So because that reduces the stray energy or external field energy. Now, then the question comes, all the spins should be randomized then. They should be randomized so that there won't be any stray field. So then what is the role of exchange? The exchange interaction try to make it align in one direction, whereas this stray field or electrostatic field that tries to demagnetize or break into domains. So then to keep a balance, there is another term that comes that is known as magnetocrystalline anisotropy. So there are many kind of anisotropy present in materials. You all might be knowing about this sort of anisotropy. So anisotropy is a kind of like that makes the properties of any material direction dependent. So in a particular direction, the property will be different. So now what is magnetocrystalline anisotropy is that the magnetic ion when present in a solid, so depending on its surrounding, it forms, because it is placed in a particular kind of crystalline electric field. So, for example, if you look at, say, Fe3O4 or any sort of magnetic ion, when it is present, so surrounding that there will be some oxygen orbitals, then another magnetic ion like that. So, if it is oxygen or any other ligands, they form a kind of electric field because they are in ionic form. So, there will be electric field, and if we try to calculate the surrounding electric field, So we have to calculate individually, and then we have to look at the effective electric field. So whatever the effective electric field at which this particular magnetic ion or atom is present, accordingly that can affect in the degenerate bands, that can lift some sort of degeneracy. So so what is the cause of this? The cause is that these are some of the orbitals. Then there are spins. So this arises. The origin is spin orbit interaction. So this particular anisotropy, also plays an important role in deciding the direction of the EG direction of the magnetization. So you must have heard something like EG axis and hard axis. So the EG axis is certain axis along which if you apply field, immediately it will get oriented. Whereas the hard axis is certain axis, if you apply the field, you need to apply more and more field to make it oriented. So if we look at certain materials like iron, cobalt, and nickel, you will see that there are some of the EG axis and some of the hard axis. Now, how do we understand what is EG axis and what is hard axis? If you look at the magnetization curve, you see that, for example, for cobalt, if we look, this is 0001. So in this one, if you apply, you see very easily it gets magnetized. You get saturation very easily. With a very small field, it saturates. Now, if you apply along the direction hard axis, this is in the AB plane. If you apply the field, this is the C axis or this particular axis. So that is the EG axis. If we apply the field along the hard axis, you will see that it takes longer field. It needs more energy to get oriented along the direction of magnetic field. That's why it is the hard axis and this is the EG axis. And similar property exists for all other systems like iron and nickel. You will see that for nickel 111 is the EG axis. So it gets magnetized very easily. Whereas along the other direction, it needs more energy to get magnetized. So what is the role of anisotropy? Now you see that if anisotropy is higher, you get higher magnetized loop because it needs more energy to get saturated. Therefore, you can see that there are some materials where the hysteresis loop is very large, whereas there are certain material where you will find the hysteresis loop is very small. And based on this loop structure, we can call the material as soft or hard ferromagnetic material. So this loop area actually defines the material into soft or hard materials. So these are all kind of like basic property. Now I will take you to certain thing like for ferromagnets, what will happen if we reduce the size of the material? So basically, we'll try to understand the magnetic property at nanoscale. So at nanoscale means, suppose you have a ferromagnetic material, we try to reduce the size of this material. So you keep on reducing. So what happens? Initially, the number of domains, because domain size is decided by magnetocrystalline anisotropy and then your exchange energy and all that. So that is fixed for a particular material. The J is fixed or the exchange energy is fixed and the anisotropy energy is fixed. So, so for a particular material, the domain size is also fixed and it is decided by those two factors. Now, if we try to break into smaller and smaller particles, then what will happen? You will come across with certain material, certain size where number of domains reduces. Now, if we further reduce it, then you will come with a single domain particle where only a single domain is present. By further reducing, we'll reach a limit where we find the particle having super paramagnetic behavior. Now the name is again misleading. Why we call this super paramagnet? This is not paramagnet. Remember, this is not paramagnet. It is still ferromagnet. And there are strong exchange interaction between the electrons present inside the magnetic ions. So still strong exchange interaction, but it is you have a single domain, and there are no domains here. Okay, so first I will tell you what is the critical diameter to reach this limit is defined by this particular factor. This particular factor, that is RST, is 36 root over of Jk by mu naught m square, where J is the exchange interaction, K is the anisotropy constant, Ms is the saturation magnetization. So this formula decides particularly this is a typical size. So at this size, it becomes super paramagnet. Now, what will happen if we reach this particular size? So you will see that at this size, I'll first tell you this. At this size, the particle is like behave, the magnetic characteristic is like this. There won't be any hysteresis. This shows a comparison between the hysteresis loop of a ferromagnet. The outer one, black line, represents the behavior of a ferromagnet, whereas the red line represents the behavior of a super paramagnet. There is no hysteresis. And random spin flap at EG axis. I'll explain this, why I call random spin flap. So look at this particular curve. What happens at a particular size, you will have some thermal energy, and this has certain exchange energy. So the thermal energy actually exceeds the anisotropy energy. This exceeds the anisotropy energy. When it exceeds, then anisotropy is not able to create any domains. So what happens? This can orient either in up direction or in down direction, and for both the direction, the energy is same. You can see this minima. This is one minima corresponding to down direction. This is another minima corresponding to the up direction. So they don't have any difference in energy, and they can either lie up or down. That's why they can. There is random spin flap. So if you don't apply any field due to random spin flap, they behave like paramagnets, but they are not paramagnets. They still have strong exchange interaction within that. But if you apply field, you find that one of the energy state is lower. That's why it attains this particular state, and you will get certain magnetization. But if you try to look at the relaxation of the magnetization, they will follow this particular relation where this KV, V represents the volume of the nanoparticle, and K is the anisotropy constant. Here KBT represents the thermal energy. Then if in this condition, if you apply the magnetic field, so this is a comparison with ferromagnetic particle. For a ferromagnet, if you apply the external magnetic field, you will see those are like domains, and for domains, no field, they are randomized, and for applying field, all the domains are aligned along the direction of the field. Now for super paramagnet, if there is no external field, you can see that they are all random direction, and if you apply the field, all moments are aligned along the direction of field. So there are certain characteristic of this material. So you can find FC, ZFC. Okay, first I will tell you what is FC and what is ZFC. Fc represents the magnetization corresponding to field cool condition, and ZFC represents the magnetization corresponding to zero field cool condition. What I mean by field cool and zero field cool conditions is that if I, before doing my measurement, if I cool the sample in presence of field and then start the measurement from the lowest temperature to the desired temperature, then the condition is known as field cool condition. And if I cool the sample without applying any field, reach the lowest temperature, then start measurement, that protocol is known as zero field cool condition. So you will find a difference. Why you find the difference? Because of blocking this particular temperature, the peak in the ZFC curve is known as blocking temperature. There are also other way of finding the blocking temperature. I will explain you while discussing my data. So at this temperature, basically the magnetic moments gets freezed at that particular point, and they don't have enough thermal energy to randomize the surface. And this loss of coercivity, I have already discussed. These are some of the examples how the superparamagnets behave. Okay, so these are some of the magnetic characteristics. Now, what will happen to the surface and interface property if we reduce the size of the material? So suppose now I will show the surface effect. So this is a comparison of the bulk with the bulk material, means big size, and with a smaller size. So you can see that if your size is large, your volume atoms are more as compared to the surface atoms. Now, when I reduce the size, you can see that the surface atoms, there are more atoms on the surface rather than in the volume. So the surface to volume ratio increases. Surface atoms to volume atom ratio increases. This can also change the magnetism of the material. You might have heard ferromagnetism in many of the semiconducting materials. Those are known as dilute magnetic semiconductors, like zinc oxide or some sort of like tin oxide or something. They also give you some magnetism. So those are basically the contribution due to the surface atoms, because the coordination number changes and there some sort of bonding has been broken. So due to that, they can give rise to some sort of magnetism. They are mostly surface magnetism that you find at nanoscale. So this is about the surface effect. Now coming to the interface effect. If we combine a ferromagnet with a non-magnet or some sort of paramagnet or diamagnet sort of thing, you will see that there is some sort of exchange interaction that present over here, but in this particular area there is nothing. But you will see that this effect extends to certain length of this non-magnetic system. So because of this, you will find some sort of magnetism at the interface of ferromagnet and non-magnet. This also happens. It also happens that at some particular point, there are two different non-magnets. Like you might have heard, or I can give you some examples like strontium titanate and lanthanum aluminate. None of these are magnetic in nature, strontium titanate and lanthanum aluminate. But when you combine these two materials at the interface, due to charge transfer, you can find strong ferromagnetism. So there are many such examples where even without any when both the components are not magnetic, but still when you combine them, you will find some sort of magnetism. now I'll come to one of the proximity effects. So all these effects are known as the proximity effect or interface effects. Now there is a particular example of another proximity effect that I will introduce you, that is known as your exchange bias effect. So what this effect exactly represent, that when you combine a ferromagnet and antiferromagnet. So basically, now I am coming to this particular effect, which generally occurs in biomagnetic systems, which is the focus of this particular talk. So this exchange effect is found in biomagnetic systems. So first observation, because this was first observed by Michelson and Bean in 1956. So they found in a particular material, when they combine cobalt, which is a ferromagnetic material, with its oxides, cobalt oxide. Cobalt oxide is antiferromagnet. So when cobalt oxide is combined with the ferromagnetic cobalt particles in a core cell structure, you can see this kind of structure. So if you cool the sample below the nil temperature of this antiferromagnetic unit, so you will find a different kind of anisotropy was introduced in the ferromagnetic system. So what is the result? I mean, why do you see, and what is the result of that? And because of this extra anisotropy, you will find a shifting of the magnetic hysteresis loop. I'll explain you what is this loop represents. You can see a dotted line and a solid line. This dotted line represents the hysteresis loop when I do the normal magnetic measurements, like zero field cool magnetic measurements. Now suppose I will do the magnetization measurement by field cooling. If I cool the sample, first I apply the field, cool the sample below the Tn. Tn means the nil temperature of this antiferromagnetic entity, and then try to measure the magnetization. So when I do that, you will find a shifting in the h-axis or magnetic field axis. This loop shifting is known as the exchange bias effect. So you can see that apart from this loop shifting, there is also enhancement in the coercivity of this hysteresis loop. And these two effects disappear at a particular temperature, that is the nil temperature of this antiferromagnet. And this effect is known as exchange bias effect. So let us try to understand this exchange bias effect from this intuitive picture. This is a picture, this is a just intuitive picture. So what happens if we apply the field below the nil temperature? You can see that this is above Tn, and we apply the field below, applying the field, we went below Tn. So this is the point over here. You have properly magnetized sample, ferromagnets, then antiferromagnets. Now you can see that the top layer of the antiferromagnet is aligned in the direction of the ferromagnetic spins. So there is exchange coupling between these two spins, this layer and this layer. Now when I change the field, I come to 0. I mean, I change the field. So, and try to reverse the spin. Like in the other case, you find the hysteresis loop. You will see that the ferromagnetic spins without antiferromagnet, they used to reverse their direction very easily. But because there is exchange interaction between these two layers, they are not easily rotating. They need extra energy to rotate. that's why you need to apply more in the negative direction. You need to apply more field to orient these pins. So now once they are oriented, when you try to reorient again, so at that time, because of the exchange coupling between this top layer of the antiferromagnet and this ferromagnet, they, with a very small field, they easily rotate and reach a state, they easily rotate. So they don't need much energy. They need less energy to rotate because of the exchange coupling between the antiferromagnet and the ferromagnetic layers. So this is a picture why we find exchange bias effect and how do we understand this. For proper understanding, a model was given. This is the model given by Michaelson and Bin. So this is, in this model, they have assumed these particular points. They considered thin film system, where they have combined one antiferromagnet and one ferromagnet. We have considered the antiferromagnet to be rigidly aligned along the EG axis, and we assume that this interface is a perfect interface. There are no roughness, no other defects over here, and there is uniform magnetization with uniaxial ferromagnetic anisotropy. So the corresponding energy can be given by this particular equation, where you can find that the interaction term with the field is HMTF cos theta. This TF represents the thickness of the ferromagnetic layer. J cos theta represents the exchange interaction between the ferromagnet and antiferromagnetic layer. And K sine square theta is the term arising from the anisotropy of the antiferromagnetic system. This is from the anisotropy of the ferromagnetic system. So now this is the energy term. So how do we find the correlation? To find the correlation, we'll try to minimize this energy. So to minimize that, we will try to minimize with respect to theta. And what this theta represents is the direction between the ferromagnetic spin and the antiferromagnetic spin. So we have considered this as the direction of the ferromagnetic spin, and this is the direction of the antiferromagnetic spin. The angle between them is taken as theta. So if we try to minimize this angle and find out what angle should be favored energetically between the ferro and antiferromagnetic system, so then we find that it is minimum for two different cases. One is 0 case, another is pi case. So these two cases correspond to HC2 and HC1 of the hysteresis loop. And the exchange bias field is defined as the sum of these two fields divided by 2, which is also equivalent to minus of J by MTF. M is the saturation magnetization, TF is the thickness of the ferromagnetic layer, and J is the exchange interaction between antiferromagnetic and ferromagnetic spins. But there are certain deviations from this model, and this is many of the cases this is not applicable. Further, there are some other models are proposed, but none of the models are fully satisfied by all the systems. So basically, these exchange bias effect in nanoparticles or in thin films are not properly understood. Now these are some of the examples or systems where we find the exchange bias effect. Although exchange bias effect has many applications, but since the mechanism has not been well understood, so still research is continuing and we try to improve the properties. Why we try to improve? Because of the applications, it has the potential for many applications. So the applications include like many of the data storage device, memory system, magnetic sensors, and biomedical applications like hyperthermia, contrast agent in magnetic resonance imaging. So there are many applications. So this is just a schematic that what kind of system it has been observed. You can have a combination of ferromagnetic, antiferromagnetic, ferromagnetic, ferrimagnetic, ferri with antiferro, ferri, or ferromagnetic with disordered layer. The disordered layer means it can be a spin glass, or it can be like some non-magnetic system, like some CDS. CDS is a kind of semiconductor. So there can be many other combinations where you will find X-ray passive. Now, some of the examples I will show. These are some of the examples where it has been found. A combination of cobalt oxide Fe3O4. It is antiferro. It is ferri. Similarly, cobalt oxide CFO. This is also a ferri. There are many other core cell structure or many different kinds of arrangement or nano architecture where you will find exchange bias effect. So now I'll come to particularly the system which we have studied. I'll skip this one. So our system is the bimagnetic system where we have combined Fe3O4 with nickel oxide. Nickel oxide is an antiferromagnet and Fe3O4 is a ferrimagnetic system. So this is a schematic overall result, but I will tell you the details. First, we synthesize the material by a very simple hydrothermal method. So this is the XRD pattern of the sample that we have prepared. You can see the reflections coming individually from the Fe3O4 and nickel oxide system. So the stars basically represents the peaks which arise from Fe3O4, and these cross marks are from nickel oxide. So apart from Fe3O4 and nickel oxide, there are no other peaks. So and no impurity phases. Also, I would like to emphasize that there are no nickel ferrite phase formed at the interface. No nickel oxide phase. So Fe3O4 and nickel oxide, they exist independently in the system in a coupled system. So then we try to understand the structural features. This is first the field emission scanning electron microscopy images. So in the first instance, when we look at the images, you can see that the images look like spherical balls, where if I further magnify this, you can see some sort of flake-like, some flakes are there. So these flakes form the outer shell of these spheres. So we assumed that probably iron oxide is at the core and nickel oxide form the shell of these balls, these spherical balls. You can see very nice spherical balls are formed. When we took the EDX analysis, we find both nickel oxide and iron oxide phases. But then we try to visualize what is there inside by the study of transmission electron microscopy. So this is the TEM images at different magnification. You can see that when you look at very low magnification, we can see the balls with this kind of hazy outer line represents the nickel oxide flakes. If I further enlarge, you can see this kind of structure over here. So, but this doesn't give you a kind of like core cell structure that we were imagining. So, but if we zoom it further at 5 or 2 nanometer, you can see some balls like this. And these kind of inside structures, this represents the Fe3O4 phases. Whereas the outer ones, you can see these are the outer ones represents the nickel oxide flakes. But the point here is that if you look at these balls, the size you can see, these are like micron size. But if we look at the size of this particular Fe3O4 particles, these particles are very small, like 11 nanometer. And the beauty of this is that when we try to calculate the particle size from our excited edges, they turn out to be 11.6 nanometer for Fe3O4 and 6.5 nanometer for nickel oxide. So that exactly matches with the size of these Fe3O4 particles we see in the TEM images. To further understand and to identify that these are the Fe3O4 and nickel oxide, we took selected area electron diffraction pattern. So from this pattern, we identify the planes. The planes correspond to, like these planes we find here correspond to Fe3O4, whereas the outer layer we can find these corresponds to the nickel oxide. So these are the individual patterns you can see. So you have we have nickel oxide and Fe3O4 phases represent, but then we find that it's not core cell structure, but there are Fe3O4 particles which are embedded within the a big area of nickel oxide. So nickel oxide is a kind of like matrix, antiferromagnetic matrix, and within that small iron oxide particles are present. So these iron oxide particles are ferromagnetic particles or ferrimagnetic particles which are embedded in the antiferromagnetic matrix. Now, this is also another confirmation we find from hard image. So here the elemental mapping. So from this mapping also we can see nickel oxide matrix is present, and within this matrix iron oxides are embedded in this one. Now with that we go to the characterization of its optical properties. So the optical properties show the absorption edges corresponding to nickel oxide, iron oxide, and also some additional band edges that is 1.8 eV. So these additional band edge could arise due to the some sort of interface forming at the junction of these two phases. So that we have clarified later on. Then coming to the magnetic behavior, so we find irreversibility in the ZFC-FC behavior, where ZFC-FC I have already explained. Now, this doesn't clearly show you what is the blocking temperature. So to find out the blocking temperature, what we did, we calculated the difference in the ZFC and FC magnetization. Then we took the derivative of this difference and then divided by the temperature. So when you do that, this is a typical method by which we can find out the blocking temperature. So we find the blocking temperature to be around 54 Kelvin. And there is also additional spin glass type of freezing at very low temperature, that is below 10 K. But if we increase the field, this low temperature freezing is completely wiped away. But we still, the blocking temperature is intact at 54 K. So with this empty characterization, we look at the magnetization loop or the hysteresis curve. This is the hysteresis curve that we find. This is the zero field cool magnetization. So we can see that it shows some sort of soft ferromagnetic behavior. This is a very soft material where the loop size is very small, and this may be due to the superparamagnetic behavior of the Fe3O4 particles. Now the same material, if we do field cooling, so we get this. So this is the field cooled magnetization. So after field cooling, we could find an enhancement in the coercivity. In addition to that, the loop has been shifted towards the negative side of the magnetization axis. This is one of the signature of the exchange bias effect. Then to further confirm this, we applied a negative field and tried to look at this. So with a negative field, it shifted towards the positive field axis. And this is a typical characteristic of exchange coupled bimagnetic system. So to know that this is not an artifact and this is really arising from the exchange bias effect, we try to measure this at different temperatures, and we find a temperature difference which decreases, where the exchange bias field decreases exponentially. So we further look at the magnetization shift, and that also we see that it decreases exponentially. So all these properties point out towards exchange coupled behavior of the bimagnetic system. Now, to further understand this, we try to do the training effect. So I'll tell you what is training effect. Training effect is a characteristic of the exchange coupled system, which shows that if there will be uncompensated spins or present spins by doing the loop. So basically how we do this, we cool the sample in field, we reach the temperature. So after reaching that, we do the magnetization cycling. So we keep on cycling. So what I mean is that we reduce the field to -5 Tesla, then +5 Tesla, then again -5 Tesla, +5 Tesla. Like that, we do the cycling many times. Okay, if we find a reduction in the exchange bias field, then this particular effect is known as training effect. And this training effect, we can further model it. So this is the modeling of the training effect. And our modeling shows that there is contribution of rotatable spins and present spins to the exchange bias effect. So this shows that in addition to the rotatable spins, there is contribution of present spins to the exchange bias system. Yes, is there anything?
So, sorry,